And the idea is this: we create basis functions, phi1 function, and then phi2 function, and then phi3 function, and so on. So we create basis functions and then represent y as a linear combination of this basis function, and then we use the right-hand side representation instead of y in the differential equation. For instance, if we have y prime times a, and then b times y first derivative, and then c times y equals g, then we replace y by these things. So this is the idea behind the method, and last time I showed everything. And essentially what you will see is phi sub I, phi sub j style calculation with sometimes derivatives, right? So I will use derivative expression this way, right? Sometimes no derivative, sometimes derivatives. So this kind of thing integrated from boundary point, right? A to alpha to beta, right? Boundary points. So this kind of calculation was done, and then depending on this calculation, we create different systems. So roughly we explained everything with examples, and if you have a question, ask me. Then, today we will study about partial differential equations. And especially, we will cover the straightforward, in some sense easiest method called finite difference method. And this method is used to solve a differential equation by simple translation. Differential equation becomes algebraic equation. And after this conversion, we solve an algebraic equation, but it isn't just one equation, it is a system of equations. So for instance, when you see y second derivative, then instead of using y second derivative, we use y n plus 1 minus 2 times yn plus yn minus 1 in first dimensional function case, right? So we use this kind of conversion to create algebraic relation, right? Algebraic relation, and then we solve this kind of algebraic relation. And roughly, when you use finite difference method, differential equation becomes the equation like this in each box, right? So there are different boxes, right? There are different boxes depending on the location, right? N could be, for instance, 0, n could be 1, n could be 2, right? So depending on location, we create the relation using these kind of things in each box, and then we solve a system. Now, instead of just one equation, we are solving a system, right? System of many equations. So this is the idea when you handle the finite difference. And this idea is the same when you handle PDE problems. So before introducing the method, let's briefly review the PDE. In this course, we don't study the theory about PDE, but at least we should know terms. So I will just copy and paste the summary notes and then review one at a time. So, take a look. We will use this kind of notation. And sometimes partial derivative can be written this way. So partial derivative is written this way, but for short, we use this subscript notation, right? U sub x sub I represents the derivative of u with respect to xi. And then if you want to differentiate with respect to these things, we can represent this way. in fact, usually the order is in fact not the same. This means we differentiate the function with respect to j and then with respect to xi. So in this sense, x of j and then x of I should have been used, but essentially when the function is continuous, then we can change the order of differentiation, of course differentiable conditions too. And we use this notation to represent the derivative of the function with respect to x twice and the derivative function with respect to y twice, and so on. And then I will use h to represent the distance in the x axis. And then similarly, sometimes I can use h to represent the distance between y. And then use of kl means u of xk and yl, right? Use of, so we determine the position and then do it. To clarify this, since later I will sketch something and then show you the point. And then to represent the derivative of the function with respect to x at the point xk, yl, we use this kind of notation, this position notation with this derivative x written here. And then similarly, we can do the derivative with respect to y, derivative with x twice, y twice, xy twice means we are calculating the values at these kind of points. All others has this kind of value calculation. And then dimensions and variables are special explanation. Sometimes we say 1 plus 1 dimension, meaning one time variable, right? One temporal variable and one space variable, right? One spatial variable x, right? While 1 plus 2 dimension means one temporal variable, right? And then 2 spatial variable. Sometimes just 2 dimension means x and y are used. Sometimes 3 dimension means x, y, z are used. And 1 plus 3 dimension means t and x, y, z. And then sometimes people reverse this, and then sometimes people say 3 plus 1 dimension, meaning x, y, z is written first, and then t is written, right? So just dimension, as far as dimension is concerned, people just assume that people understand the concept already. So for instance, when you see the function, you don't have to explain the input dimension. Take a look. If you have a function like this, input dimension is what? Automatically 2 dimension, right? This is 2 dimension. This, and then if we sketch the surface like this, then it's 2-dimensional surface, right? It's 2-dimensional surface like this, and then 2-dimensional surface like this can be written in 3-dimensional space, right? In 3-dimensional space, we can represent 2-dimensional surface. Then eventually, it becomes 3-dimensional object, right? This whole thing becomes 3-dimensional object, even though this is 2-dimensional. Essentially, 0 dimension is point, 1 dimension is curve, 2 dimension is plane or surface, and then 3 dimension is volume, right? Volume. So roughly, this is the definition, and we assume that you completely understand these things. But if you have difficulties, you can always ask me to check what is going on. But at least we have 2 input dimensions, so 2-dimensional, and then 1 output dimension. Or sometimes time dimension can be represented or omitted, right? Time can be represented or omitted. So for instance, as I mentioned before, assume that we just say y of t equals t squared plus t. Assume that this is the given function. Then y is a 1-dimensional function, right? Y is a 1-dimensional function. Then because it's 1-dimensional, do we represent this by a line? We rarely represent a function, even though it's one-dimensional, by just a line. If you do, then what should we do? We should represent the position at time equal to 0, at time equal to 1, and time equal to 2, and so, right? So if we use these things, then we should represent the position using this kind of notation. But this is not easy. Because of this reason, even though it's one-dimensional function, when we express using graphs, we use two-dimension, right? Do you follow me? So suddenly, y itself is not written in just one dimension. It is written in 2D, right? It is written in 2D. So it is written this way. Right? It is represented by this kind of graph. So I assume that you completely understand this concept, but if you have difficulties in dimensions, you can ask me. Any questions or difficulties in dimensions? So there are many, many situations. For instance, input could be just one dimension, and then output could be 3 dimensions. Do you follow me? Right? Input could be one dimension, but output could be 3 dimensions. Then to represent this kind of thing, we should use 3-dimensional space, right? And then in 3-dimensional space, we represent this trajectory, and it is usually a 3-dimensional curve. This object itself is 1 dimension, right? But it is written in 3D. It is represented. So we will assume that you completely understand this concept. And in addition to these things, time can be both sketched or omitted. Time, right? Time can be sometimes sketched by using an axis or omitted. For instance, take a look at this case. In this case, time is not sketched, right? Time axis is not even sketched, right? Just we sketched y. But take a look. Here, time occupies this 1 dimension, right? So we will use these kind of things in the course. So we are not handling 2 different things. We are handling the same thing, but here we omitted time axis. Here we represent time axis. So if you have any questions up to this point, ask me. So no questions? Then roughly this is the idea. When you have derivatives, we use finite differences. That's the idea, right? So differential equations involve these kind of terms, right? Differential equations involve these kind of terms. And instead of using these kind of derivative terms, we use finite differences consisting of just terms with minus, right? With difference, right? Difference with division or something. What is the similarity and difference? The quantity might be very similar, right? Quantity might be very similar. What is the difference? This involves derivative. This doesn't. This is just plus and minus stuff, right? Just number minus stuff. So this becomes differential equation because of this, but this becomes algebraic relation or equation. So we convert it using this thing. So in some sense, finite difference can be easily studied by just doing this thing. And later, we will handle the convergence step for specific cases. So any questions up to this point? The next thing is the actual convergence. Assume that we have the derivative function at the position I. So do you understand the meaning? The meaning of this kind of thing, right? The meaning of this kind of thing is calculated at this point, right? So we have differentiated the function and then check the value of the derivative at I position, xi position, right? And then it is written this way. And then we can do the differentiation the same way, or second derivative, and so on, right? So these were all questioned on the exam, right? And then we can expand it. We can extend this definition to two-dimensional functions, right? At any point we can do this. So x derivative can be written in this way, y derivative can be written in this way, and take a look. Plus 1 is here, plus 1 is here. So difference is found, right? And then xx, and then yy. So roughly these are the cases. Then what kind of partial differential equations will you handle? We will handle this kind of differential equation. Linear advection equation, written, is too high, right? Written in this pattern, right? So take a look. We differentiate u with respect to t. We differentiate u with respect to x, and then link them, right? So this is the heat equation type, and the real heat equation is given here, right? And then this means we differentiate t with respect to time, right? So 1, and then t could have n dimension, right? I introduced this notation here, right? This notation is differentiating the function with respect to the given spatial variables, xx, yy twice, right? xx, yy, z, and so on. And the Laplace equation is given the same way, right? We differentiate u with respect to the given variables twice and then add them. And Poisson equation changes this to some function. And the wave equation differentiate the function with respect to t twice, right? And then write the right hand side. And as you can see, what is the similarity and difference? What is the similarity and the difference of these two? As you can see, the second derivative does not appear on the left hand side, second derivative appears. So this is a difference. And we will handle the Dirichlet problem, and then this Dirichlet problem has boundary values. For instance, assume that we are handling a differential equation in this kind of domain. Then we at least know the values at boundary points, right? At these boundaries, we know the values. Then it is called the Dirichlet problem. Right? We know the values. And if we have the mixture of initial value and boundary, or if we have mixture of boundary, right? At some point x, y, we know, right? Assume that these are boundary points. If these are boundary points, then we know the value. Then it's Dirichlet problem. But assume that we have mixture of this, but at some other point, for instance, at this point we don't know the value, but at this point we know the outer normal derivative, then we say it's Neumann problem. So sometimes I may not go to this part, but theoretically knowing this might be helpful, because later we'll finite element method with this kind of thing. So sometimes we know the value, or sometimes even if we don't know the value, we know this outer normal vector derivative, and then that. So you should not be misled by this notation. It doesn't mean anything, just a box, right? Just a box, right? So sometimes we have boundary values at every point, but sometimes we have missing boundary value, but this is compensated by this kind of outer normal result. So roughly these are the steps we handle, and yeah, it is already written here, right? Neumann problem. And then we mix these things too, and then sometimes we need to handle repeating points, especially when you handle heat equation. you should have second derivative in the time direction, but we don't have enough information to go back. We have the initial starting point, but we cannot go back. Then we should repeat the starting point twice. Then we should use this kind of derivatives. So we will use repeating points when we handle heat equation. Heat equation should be handled this way. If you don't handle the heat equation this way, your result will be useless. And then I don't know whether we will have enough time to handle irregular boundary. Sometimes our boundaries are nice. Our boundaries are nice. Like rectangular boundary is nice. But sometimes we may have this kind of boundary. Then assume that we divide it. Then, as you can see, we say, for instance, this to be U5, right? U5. Then this point should be U4, right? U4. And then this point becomes U3, right? Because this point is outside the boundary. We label it this way, right? This is U3, this is U4, this is U5, U6, and so on. Do you follow me? So sometimes we have irregular boundaries given by the problem. Then the derivative doesn't have this kind of uniform distance, especially the denominator part doesn't have uniform distance. So we will define irregular boundaries, and then distance is used instead of h. Right? Instead of using uniform h, we use this distance in the denominator. So once it happens, I will revisit this part. And then when we handle PD problems and then when you use program to solve the problem, we should be very careful. We just think this will be correct and then run, but suddenly an unexpected thing happens. The result can blow up. Why? There is a very simple reason, and generally handling this kind of situation is called CFL problem. Three initials of three people named. I don't remember any name, but there are three people involved in this direction. And then roughly, when it appears, I will explain. The major idea is this. Assume that we are solving a differential equation, and then let's say x is the spatial variable, and then time variable can be omitted or sketched. So I will introduce time variable. And then we are solving this differential equation. Then we break up the interval. We break up the interval in time direction and the x direction. Right? Time direction and x direction, and then we know the value at each point, right? We want to know the value at each point, so we say, oh, this is U11, and this is U21, this is U31, this is U41, and then you say this is U12, and then this is U13, and so on, right? So we label them, right? For convenience, even though we know boundary or something, we sometimes attach this kind of value. Or we call intentionally this kind of thing 0, 1. Then programming will become easier. I'm sorry, 1, 0. U10 here. And then U20 here, U30 here, U40 here, and so right. So sometimes we just name these things even though we know the boundary values. So somehow after dividing the spatial variable and then temporal variable accordingly, you run the program, but suddenly your result may blow up. Then you may think, oh, theory has a problem, but it's not the theory part. It is the part designing this kind of direction. So to avoid this problem, what should we do? To avoid this kind of problem, we should refine this kind of interval. We should refine this kind of interval. Then we may get a reasonable result instead of. So this is the key part of CFL condition. In other words, with rough t-directional division, we may have divergent result, but with refined result like this, we may have convergent result. Of course, I'm not saying just by dividing 4 more times we get the result. No, sometimes 40 more times or 400 more times you should divide in this way. And then I will let you know the reason very soon. So sometimes people learn about this kind of technique and then blindly apply the technique and then get very strange result. Why? Because they didn't take the course like this and then didn't learn about this kind of CFL condition. So you should refine these things so that the result does not diverge. So a very rough estimate is this. Very rough estimate is this. Usually when we do something, then we represent UI plus, oh strange. UI plus 1 j minus UI j over h, and then I will use specific case instead of general case. Assume that you are solving this differential equation, right? Simplest case, right? Simplest PDE case. Then you should break up the u part and then, I mean the time part and then x variable part. Then in x, ux can be written this way, ut can be written this way. So I will be more specific. U I j plus 1 minus u I j over delta t, right? To specify the direction, I will use delta t instead of just saying h and k and so on. So I used finite difference of u's of t, and then now I will use finite difference of u's of x. Then I plus 1 j minus u I j and then delta x. Any questions up to this point? Then you may solve this for instance, this one. What is the result? Can you solve this for this? So roughly this is the situation. Then, without considering CFL condition, assume that you just pick your own random delta t and delta x and run. Then if you are lucky, you may get a result, nice result. But if you are not lucky, you get some divergent result, right? Some number, the result goes to infinity, like very big number. So, roughly speaking, of course later I will refine the result. Roughly speaking, this kind of ratio, in this case it's a different situation, but roughly this kind of result should be small enough, or generally CFI can do. So this is the situation. take a look. This value comes here, u I plus 1j, u I j is the case. But take a look. Assume that this kind of value is too big. If this kind of value is like over 1, right? This kind of value is over 1. Then the next value here is the sum of these two, and somehow this value over 1 multiplied by this may increase this value, and then next time the increased value is used here to increase more, and then this kind of thing happens, and then later your result here will be very unreliable. So theoretically it looks fine, but practically if this value, this kind of ratio is too big, then we may be in trouble. So there is a limitation of this kind of value. Of course, depending on equations, we have different limitation, but roughly it's not a good idea to have big number here, especially 1 or sometimes 1/2 or sometimes some. I will let you know the details later, but have the big picture. So if you want to use this method to solve this problem, I will explain. If you want to use this method to solve this PDE problem, you should divide correctly. Almost anybody can memorize this thing or even derive this thing, right? But if you use wrong ratio here, your result will be unreliable. You should have correct ratio. In other words, then I will divide the time direction, right? This is time direction, this is x direction, and then initially someone think, this may work. Someone may think this may work. If you divide this kind of way, then roughly delta t over delta ratio is almost like 3. Do you follow me? Roughly this over this one ratio is almost 3. Then it's like this. You are multiplying 3 and the next time, roughly like doing this over and over again, right? Right? 3x, and the next time 3 times 3x, and then 3 times 3 times x goes on and on and on if you run it. Then what happens? This result will blow up. Very unreliable. So roughly, this kind of situation happens. So what is the problem with this design? The design had this ratio too big. So how can you make it work? Let's divide more. Let's divide like 6 more times, right? Roughly 6 more times. So we divide t direction more times, right? So roughly this kind of thing, right? We divide more times. Then this ratio will become 0.5, right? Then what are we doing? Roughly, we are doing x and then 0.5 multiplied by 2 terms, right? If you have 2 terms, the worst case is having 1 and then -1 subtraction. Then 1 minus -1 is 2, right? So even if we test the worst case, 1 minus -1 case, with this product we will not have big result on the left-hand side. So roughly, you should be very careful. So you may think, everything is fine in program. Why doesn't it work? Then I say, you ignored CFL condition. CFL condition asks you to divide this accordingly. Right? So do you follow me? Of course, you don't have to understand the details at this moment, but roughly this is the situation. And worst scenario may happen like this. Assume that we begin with a number below 1 or less than or equal to 1, then this kind of thing is the worst scenario. Somehow this value is 0.99, and then somehow this point could be minus 0.99, right? Assume that this thing happens. Somehow this value initially begins with some number between -1 and 1. But the worst scenario is having 9, and then this having minus 9. Then if you add these things, then it is 1.98, right? this sum could have 1.99, almost 2. So if this factor does not reduce this number, then the next step, next number will be large, right? Almost twice larger. And then it comes back, and then similar thing may happen. Then each time, it is like exponential growth, right? Always twice larger, twice larger, twice larger, and it will blow up. So how can you remove this problem? Just by designing well, right? So you should divide this carefully. So in the past, I asked the students to intentionally divide it like this. So sometimes I ask the student to divide using this number and then divide it using this number. This is nice. This diverges. So I asked this kind of problems before. As you can see, it's minor difference, right? 1, 3 and 1, 2. It's a minor difference, but this converges, the other diverges. So it heavily depends on the design. So it's safe to, in this kind of situation, it's safe to use t equal to 0.000, like 0.5 or 1.0, right? About these are okay, right? This kind of design is okay. But any number bigger than like 1, 2 might not work. So when you divide this step, then each height should 0.00012. Next height is 0.00024. And this is okay, right? 0.00036, right? This design is okay. But if you divide by using 1, 3, 1, 2, 6, and so on, then it blows up. So this condition is good. So in some sense, after doing all the steps, the crucial thing that you need to remember might be just this thing, CFA condition. Because almost anybody can design finite difference algorithm, very easy. But people who did not learn may use some strange number here, and eventually let this thing blow up. So roughly, I overviewed the things that we will do in the course in about 1 or 2 weeks. And please check whether you completely understand everything up to this point or not. If you have doubts or questions, ask me. If you don't, then I will solve one at a time.
Can we go back over to that setup of the problem with t equals 0x?
All right, let's go back here.
On the about the third line down, I'm not catching why the increments are different on both sides there. In other words, on down third line you get a u of I j plus 1. And on the right side you get a u of I plus 1j.
So the reason is this. We have two axes, right? X-axis and t-axis, right? X-axis. And then in t-axis, we may evenly divide the interval, and in x-axis we may evenly divide the interval. So we are not limited to some number. We can freely choose any h, right? Any distance, right? So assume that I choose distance like 0.1 or 0.01. So initially I decide to use, I will use spatial distance 0.01, right? And I want to choose time difference between, so I decide to choose this way. Do you follow me? So when I design, I can break up the interval as I want, right? So I can break up the domain as I want, right? So I have a domain like this, right? Then I may break up the domain this way or refined way, right? So it's up to me to decide this kind of distance in x direction. So I may slice any I want in the time direction or in the spatial variable direction, right? In the x direction. So to represent this situation, generally I used delta t in the time derivative direction, right? Time derivative direction I used delta t, x derivative direction I used delta x. So this distance is called delta t, right? This is delta t, and then delta t. And then this distance, right? This distance is called delta x. So I may divide it by using delta t and delta x. So I may choose any number in this direction and in this direction. Any more questions? So it all comes from the definition of the finite difference derivative, right? It's generally this form, or in specific form, this kind of thing, right? This is the derivative, right? When you represent the derivative, we use this thing. And then h in the direction t is called delta t. H in the direction x is called delta x, right? So it comes from this one, right? When we can replace the derivative by this kind of difference. So I replace the derivative by this kind of thing, right? I replace the derivative by this thing. And then afterwards, I just solve it. Any questions? So roughly, as I mentioned, we can avoid this kind of bad situation by using small number here. And in fact, there is a chart for this type of equation. Use this value smaller than this. In other words, when you break up the domain, you should break up accordingly, right? CFL condition. Then let's begin. So this is the situation. We are solving a PDE problem in the domain. Then there is a solution called U, right? U is a solution in this domain. And once X position and T position, right? So this generic position, right? Once X and T position is given, we know the value of U, right? We know the value of U at this position. So that is our goal, right? Once we solve the differential equation, we know the value of U at the position. But we do not know the value before solving the equation. After solving the equation, we know the value. But before solving the equation, we don't know the value. In other words, that U becomes unknown, right? That U becomes unknown. So U value here, U value here, U value here, we don't know, right? We don't know these U values. Right? Once we solve the differential equation at generic position xt, we should know these kind of U values, right? We should know these kind of U values at any point in the domain. But we do not know these kind of values at all before solving a differential equation. After solving we know, but before solving we do not know. So what do? We name these things, right? So what we do is, instead of using randomly distributed points, we name the points. Oh, let's say this first point is U11, right? And then let's say the second point, I will use a little bit bigger picture. So let's call this position U11, right? Let's call this position U11. And then call the evenly divided next points U21, right? And then we call the next position U31. And the next position U41. And then we use the same idea in the vertical direction to U12, U13, right? We represent these kind of unknown heights using letters, right? So now even if we do not know the values at these positions, at least we know the name of this value, right? We do not know the value yet, but we know the name of this value. The name of this value is what? U11. The name of this value is U21. So at least we know the name of the results, right? Then, now the thing is determination of these named things using values, right? By solving an equation, we want to determine these names. What name has what value, right? This name has what value, this name has what value. At this position, we don't know the value. Then now, how can we create the relation? We create the relation from the differential equation. Assume that, so this is a t direction, this is x direction. Assume that u sub t is given in the differential equation, then this can be translated, right? This can be translated into the finite difference representation. So u12 minus u11 over this distance, say delta t, right? At 0.11, right? At 0.11. At 0.12, right? This thing is at 0.11, right? 11 is not actual point, it's just index, right? These are indices, and u sub t, by the same reasoning, u sub t 1, 3, 1, 2 over delta t means 1 at the point 1, 2, right? 1, 2 is not the actual number or actual coordinate, it's just the index, right? In index system, right? So we represent ut this way. Take a look. Ut at this point is this one, right? But the same ut at this point is this one, right? And similarly, ut at this point will be different, right? So we can, instead of using 1, 1, 1, 2, 1, 3, 1, 4, and so on, we use generic position. So let's say at generic index ij, at ij index, what happens? ut is represented by what? Ut is represented by uij minus uij, right? So we represent the derivative by this. So at each point, the representation of the derivative varies. So this is valid. This representation is valid only in this, right? In this area, right? Only in this area. And this is valid only in this area, right? So we do not have uniform difference representing ut. We may have different things like this, generic. So at ij position somewhere, we have this kind of difference, right? At ij position, we have this kind of representation. So we represent ut by this. And then if we just change the role of axis, ux can be represented the same way, right? Do you follow me? So we essentially represent the derivatives at each point, right? At each point, or neighborhood of each point. So the differential equation gives us the equation of these things instead of derivatives. Do you see any derivatives here? No. Take a look. Let's return back. What is u sub ij generally? U sub ij are just numbers, right? Names, right? Names at each point, right? Names at each point or numbers. So here we have derivative. Here we do not. We only have just numbers, all numbers, right? So this part is differential equation, this part isn't. The differential equation becomes equation of numbers or algebraic equation, right? Algebraic equation or system of algebraic. So this is the key idea. And I will be very slow. If you have a question, ask. Then let's convert it accordingly. So we are solving the differential equation ut equals ux, or even some number can be multiplied. So let's make it a little bit tougher. Let's multiply by k. Right? K is a number. We are solving this kind of differential equation. Then at generic position ij, it is not coordinate system. You should not be confused. We just use index ij. Index ij means, depending on your system, for instance, I will explain this first. If you divide by, it's like 1/3 and then 2/3 or 3/3 and so on. And if you divide this by 1/5, 2/5 and so on, right? Then what is the meaning of 3, 4? What is the meaning of 3, 4? In the x direction, we go 3 units, right? In the t direction, right? So this is x. Sometimes you can even switch t and x. So I always presume you understand this situation, or you can even design this. So assume that this is used, then it means what position? This position, right? So 3, 4 means what? Index 3, 4 means what? Index 3, 4 means what? In the actual position, 3/3, and then 4/5. Do you follow me? So you should not be confused between the actual point and index. Your index system is used to locate the position, right? Locate the position. It does not mean its actual point. In other words, when you have 3, 4, it does not mean the position is 3, 4. It only means your index says the position location is 3, 4, not coordinate system. So if you don't understand, ask. So 3, 4 means it's not actual position 3, 4. It means in this kind of situation, 3/3 and 4/5 in this kind of situation. So if you design differently, your index may indicate different position, coordinate-wise. So when I say ij, it means index-wise, right? Afterwards, I don't even explain this thing, just assume that you understand this concept. Right? Index-wise ij position, then ut can be replaced by ui plus I, and then j plus 1. J plus 1 minus ui j over delta x, delta t, whatever delta t I may choose, right? Later I will pick delta t. So in this case, what is delta t? In this case, what is delta t? In this case, what is delta t? 1/5, right? What is delta x in this case? 1/3, right? Equals k times now ux u sub I plus 1 j minus u sub ij delta x. So please browse this thing and ask questions if you have difficulties. Then this is the situation. Now I will show you how computer follows your algorithm after simplifying this. So take a look. U I j plus 1 equals, right? If we solve the equality for this, then u I sub j I comma j plus 1 is equal to uij plus k delta t delta x, and then ui plus 1 j minus uij. Right? I just solved it. Then this is the situation. Generally, when a differential equation is given, boundary conditions are given, right? Boundary conditions are given. These points are all known, right? By the boundary condition, right? All known. Then, take a look. As far as second index is concerned, nothing advances, nothing on the right-hand side advances this number, right? Every number, every index on the right-hand side, every second index on the right-hand side does not exceed this one. So we can represent this thing using this kind of explanation. So we do not know this number yet, right? We do not know this number yet, but we know these numbers. Then take a look to determine this number. So I'm magnifying this part, right? I'm magnifying on the right, and then we know these things. Right? We know these things roughly. Then take a look on the right hand side. What terms do we use? On the right hand side, uij is used, right? This is uij, right? Uij is used. And then this is ui plus 1j. This is one, right? Right? And then uij is used. Right? Do you follow me? ui, this position is uij, this is I plus 1j, this is uij plus 1, right? There are three positions used here. So uij is used, ui plus 1j is used, and then uij is used. And then these things will be used to determine this unknown. So we usually create this kind of stencil. Right? This is a stencil. Or generally, in short, people represent it this way. Right? These two things are used to determine this thing. Or sometimes people reverse this thing. Oh, unknown is represented by a circle, and then, so sometimes people use this kind of stand. So as far as the meaning, is understood, no matter what shape you use, it doesn't matter, right? Roughly, this is the situation. So by using these two numbers, you can determine this number. So take a look and then ask questions. Yes?
So that's only the forward difference?
Right. When you decide to use forward differences,
We use central difference mostly.
if you have second derivatives. And this kind of thing has special names like upwind, but I don't want to force you to memorize this, but it doesn't matter. I'm just giving you the idea, and then later, after learning all these things, I will refine and then let you know what kind. So for this x derivative, for this t derivative, I used this kind of thing in forward direction. Then as you can see, these numbers are known, this is unknown. Right? These numbers are, this is unknown. These are known, this is unknown. Because these are known, we can determine it. So I will track down the calculation steps. So assume that you are a computer and that your computer is programmed by some people. Then initially these are all initialized, right? Or given by the boundary value, right? So these are all known, right? Because boundary values are given and the differential equation problem is given, right? All these are known. Then using this stencil, this will be known, right? So it becomes suddenly known, right? Do you follow me? And then next step, this will be known, right? Next step, this will be known. Next step, this will be known. Next step, this will be known, and so on, right? So next step, so I will just start, right? This will be known, right? And the next step, this will be known, and so on, right? And so on, this will be known, and then eventually we solve it. So please browse these things and let me know. every semester, I've taught finite difference method more than 10 semesters. Every semester I saw some people doing this differently. I saw people doing this way. People just think, even though this is not even determined, and then people say, oh, in this order people program. Do you follow me? If you program this way, it's garbage. Even if it looks very similar, it's garbage. Why? These are not known. Take a look. These are known. Right? These are known. These are not known. But somehow people program this way. Of course, when you design your program, you don't know what is going on behind. Just make something and then run, but then eventually what you do is this kind of thing. But these are not even known. So you should not program this way. Even after I warned these things, I had seen a lot of stuff like this before. Almost every semester someone programmed this way. So do you follow me? You should be very careful. You should know what is known, what is not known. In other words, this stencil is correct, but if you somehow try to use the other stencil like this, then you will be in trouble, right? Right? If you try this kind of direction, then you cannot solve it. So in spatial direction, we know, right? In spatial axis, we know the initial values, but in time direction, we don't know. Then how can you rely on this result in the time direction to advance? It's impossible, right? So if you go this way, initially these are somehow useless results. For zero value, then everywhere is zero. Or some unassigned values, then it may blow up. Anything can happen. So when you program, you should know what your program does, right? You should not even send it to me. I have a harder time than you to read your programs. So roughly, I, in some sense, completely explained the idea other than this number, right? So later, I will give you a chart doing this. But use small number initially, right? What kind of limitation might be okay? There is a limitation calculated theoretically, but do not worry. Like, just use some numbers smaller than 1/2, right? Why? Because there are two terms. If you make this smaller than 1/2, then it will not blow up. So roughly, this is it for the first order. So before going further, I will check whether you understand the dimension. So in this kind of situation, how do you call the dimension? What dimension problem? 1 plus 1 dimension, right? Do you follow me? One spatial variable, one time variable, or one time or one spatial. 1 plus 1 dimension problem. And to represent this solution, there are in fact three ways. One way is using input axis like x-axis, input axis, t-axis, and the result, right? Roughly u, right? So to represent this result, sometimes people can use three-dimensional graphs, right? Three-dimensional surfaces representing the solution. So this is one way. Second way is using this height information, right? I will go to the next one. So I will go to this. Second way is representing the heights, right? So x and then t is not even, we don't even use three-dimensional value. So just representing heights, right? So initial value like 1, like 1/3, 2/3, 3/3, 4/3, and so on, right? So these are the values, and then 1/5, 2/5, and so on, right? So these are all divided by you, right? You decide this kind of division, and then heights are given, right? So at this point, 3. At this point, 2. These are heights, right? At this point, or sometimes people use u equals 3, u equals 2, u equals 5, and so, right? So this kind of representation is possible. So the one that I explained, 3D graphs, make this kind of thing easier, but at least you can know the meaning, right? Finally, some people don't even use time axis at all, right? Time axis at all, just x-axis, just x-axis. Then it's way tougher, right? So, for instance, time equals 0, then it has like 3, 2, 5, and so on, right? And then time equal to 1, like 4, 1, 6, and so on, right? So you can write this way. And you can use any kind of combination, right? You can use any kind of combination in this direction, or even animation. So we are not very interested in the representation of solution. We are more interested in the determination of u values, right? So finite difference method does this, determination of u sub ij. In other words, it determines the actual height or actual value at each point, right? So we are interested in the determination of this kind of values. We are not interested in the presentation or representation of solution. In other words, when you submit your homework, you have freedom of representing your solution anyway, unless it is specified. Some problems have specification. In other words, I ask you to animate. Why? I want you to see the movement of the solution. For instance, as soon as you solved heat equation, then I want you to see how it dissipates, right? How it moves, right? Heat moves. Heat moves, right? How somehow temperature changes. So do you completely follow me or not? In other words, in this course, except a few cases, I don't care what kind of solution representation you use. I care about the actual height at each point, right? What is height here? What is height? This is a good point to do it. What is height here, right? What is the height here? What is the height here? What is height here? Or what is the value of u here? What is the value of u here? And right? I'm interested in this thing. I'm not interested in other things. In other words, if you submit your solution, unless it is specified, just you can say u11 is something, u12 is something, right? Doesn't matter. So please browse this case, right, and ask me. If you don't, then I will pause and then maybe we can take breaks, but at least ask questions. You should, because this is the beginning, but at the same time, this is everything. Other things are just minor tweaking of this stuff. No questions? Then let's take an early break. So let's resume at like 3:58 or something like that. I cannot see the angle, correct angle. So let's resume at 3:58. I mean 2:58. 2:58. Questions? If you have any questions, ask me before going to the next case.
Can you show us an example of a boundary condition where we know all those values there?
I see. For instance, So what do you want to? X first or t first? It doesn't matter. X first or t first. Sometimes people use tx, sometimes you use xt. It doesn't matter. So what do you want to use first? T or x? T. So I will use this direction, right? So first argument is time. Second argument is x. Then so the boundary condition can be given this way, or initial, in this case initial. In two-dimensional space, if we use initial condition, then it also becomes boundary because it is t is the axis, right? So in this case, this kind of initial condition can be given, and then for time running from 0 to 0.001, right? So this could be the problem, right? And then x boundary can be given. So I will solve one problem with you. Any questions? So we are solving this problem. Then let's design. So design step is important. So I will design the domain, x direction, and then it should be from -2 to 5, right? -2 to 5. And then time direction, about this is 0, right? About this is 0. Time direction, we have 0 to 0.001, right? So I will use like 0.0005 and then 0.001. Do you follow me? So I broke up this way. And then I will break up this way. Then we now created grid system, right? So I will show you the grid system. Instead of really sketching it, I will use just boxes. So this point we know, this point we know, and then this point we know. It's not very unlucky because it occupied the space, so I will remove this thing, remove this thing. So as far as grids are concerned, we want to know the values at these heights. So this is my design. So at least how many unknowns do we need to solve this equation? How many unknowns do we need? 14 unknowns, right? 14 unknowns. Or 16? Right, 16. 16 unknowns, right? So let's call this U11, U12, and so, right? I mean U21, sorry. U21, U21, U22 here, and then U31, sorry. Three one, 4 1, 5 1, right? 3 1, and then 4 1, and then 5 1, and then U 1 2 here, right? And so on. So roughly we need these many unknowns, right? So we just name them. We don't know the value, we name them. And For convenience, I call this intentionally, I call this what? U, excuse me? Right, t-axis is 0, right? 0, and then 0.0005, and then 0.00. But it is known, right? What I meant was unknown, and these are known. But for convenience, even if these are known, I will write it this way: 20, U30, U40, U50, U60, U70, U80. Do you follow me? I'm just showing you the design step. Then what is U10? What is U10? Yeah, because of this, what is U10? So U10, I will write down the meaning of U10. U10 means U of 0 at point -2, right? Do you follow me? And U of 0 at point 2 is what? 10 times -2, so -20 is the height, right? At this point, it is -20. So similarly, what is U20? -10. What is U30? 0, right? And so we can determine this. And then using these things, we can go up to U11 by using the same idea. Right? So roughly this is it. I'm showing you the design step. And as you can see, delta t over delta x is small enough, right? We will have no trouble, right? Delta t over delta x is small enough. So I showed you the design step, and if you have any questions related to this case, advection equation, ask me. Then roughly, from this point on, it will be very boring because just the same thing over and over and over again. So later, you will want to know about theoretical stuff. What about CFI condition? What is the break-even point, right? That kind of critical point. In other words, how should we consider the ratio of this number, delta t over delta t? How should we do that? So later, you may be interested after you are completely bored. Mm-hmm.
How would you derive that?
So let's go back to this equation. So how can you determine U11? So I will show you how to do U11. In fact, if we have enough calculation power, we can do it. So please let me know what these are. I will use this space. U1 0.1 equals U10 plus K is 1. Delta T is given, right? Delta T I will use, and later replace this by numbers. And then U21 minus U11, right? And from this, we got this thing. Of course, you don't really write this in your program. Just read these things and calculate the value. Thank you. So J is 0, right? J is 0. I is 1, J is 0. U11 means I is 1, J is 0. So let's use this thing to calculate U11. So from this, we will calculate U11 really. So U11 equals U10. U10 is -20, right? U10 is -20 plus delta T is 0.0005. 0, 0, 0, 5. Delta x is 1. And then u20 is minus 10 minus u10 negative 20. Then what happens? Negative 20 plus this number, and then if you do this calculation, 10, right? So minus 20 plus 0.005. So the result is negative 19.995. So this is the result. Of course, you don't really see this if your computer program runs these things to calculate it. Do you want to calculate the U21? So if you want, you can do it, right? U12, yeah, I guess U12 is the next one, right? U12, I'm confused. No, let's look at it. So I want to calculate U21, U31, U41. So you should know the order. Your program should not be created vertically. You should not create this way. This is wrong, right? Wrong. Completely wrong. Your program should traverse this way. Of course, this is the initial condition, and then after calculating this, this is the next one, and so, right? So you should go all the way through, right? And then go all the way through. You should program this way. If you program the other way, you will always get blowing up result, or zero result. Sometimes 0 is assigned, then 0, 0 all the time. So please browse this problem and check whether you can really do it or not. No questions or problems?
I'm sure we'll have someone to start doing it. But no, it all makes perfect sense right now.
Do you assume that you know the value of equals 0, x equals 6, and anything that last 20
So that's the reason why we usually have limitation in the problem. We have the limitation in the problem. So we give boundary values, right? So negative 2 to 5 is known, but outside we don't even use, we don't even rely. Good question.
So if you're using the tuple replace on the row 0, how do you find that last 20 for the
Yeah, good question. Good question. Yeah. So in this sense, our result may have limitation like this, right? May have limitation like this. Good question. Limitation like this, right? Yeah, you're right. So sometimes we cannot find all the values unless boundary conditions are specified. So usually when the problem is given, sometimes like heat sink condition is given. You have a heat sink here or something, right? So always the boundary, once you arrive at this kind of thing, heat sink condition could be given, right? Or some kind of condition is given. Good question.
In this case, that's time. Vertical axis is time.
Right.
You just extend x, the x boundary of the show by 1,
Right.
extrapolate it over.
Right, and then yeah, do the thing. Yeah. So there are many ways of handling it, but in this course, we don't want to worry about some minor problems that may happen. There are many ways of handling it. Sometimes we can use heat condition. In other words, we don't have any changes. In other words, anything appearing here could be 0, or some function could be given, but good point, right? So in this sense, we rely on these kind of values, right? Any questions? Then let's go to the next case. In this sense, you know almost everything. Once you clear these things, others are just variation of this thing. For instance, assume that you want to solve heat equation. So assume that you want to solve a heat equation. First of all, before solving it, I want to check whether you know the dimension. What is the dimension of this problem? 1 plus 1 dimension, right? 1 plus 1 dimension. One time variable and one spatial variable. Then, without even an explanation, so most people don't even write this kind of thing, right? This indexing, just write it directly. U I j plus 1 minus uij over delta t equals, you can even add some numbers such as c squared here, right? Doesn't matter. This is, right, ut part, and then ux part can be written this way. Take a look and then ask questions. No questions? Then let's equate this thing. Ut is equal to uxxor. This is equal to this one, right? Ut is equal to uxx given by the differential equation gives us this relation. So uij plus 1 equals uij multiplied by delta t over delta x squared multiplied by ui plus 1j and then minus uij plus ui minus 1j. So I don't want to sketch the full domain graph. I want to just sketch the stencil. So what we don't know is this point, and then to find this point, we use this point, right? We use this point, and then advanced point in the spatial direction, right? And then previous point. So this is the stencil. So to determine this thing, we should use this. So if you have a question, ask me. If you don't, then I will give you an example.
You just did it in the very last part again. Use to get the little pencil drawing.
You want to know the reason why?
Yes, how did you get that?
So this is the generically ij position, right? This is ij position. So assume that this is ij position. Then it is one up, right? One up, right? And then this is one right hand side, and this is one left hand side. If you assume that this is ij position. This is the ij position. Then we can create a stencil like this, right? J up, right, and so on. Then I will briefly show you the possible problem of this type. Solve the differential equation with the initial condition right? The initial condition like this, right? And x is from -2 to 5. And then t runs from 0 to 0.01. So this is the question. And then heat sink. So heat at the boundary, x equal to -2 is 0 always. Heat at the boundary on the right hand side is 0, right? So we have heat sink on two sides. Or heat, instead of heat sink, you may give heat function there too. So for instance, we have some kind of steam here, right? Depends on your environment. So all the conditions are given. Do you follow me? If you don't, then ask me. Then let's solve it. I will design. First of all, we should write the domain, right? So domain is from -2 to 5. And then hopefully this is 0, right? And then this is 0.01. So I will divide this by 4 subintervals, right? So this is 5 might better. 5 might better. So 0.002, 0.004, 0.006, 0.008, 0.01. So it is my design, right? You may design differently. Right? You may design differently. And then we may break this up. So you may break up any way you want, right? Any way you want. And then we call this U11, and then U21, right? U21, U31, and so on, right? Similar, right? And then I think it's not a good idea to use 0 position here, so I will shift. So I will call this U01 intentionally. Maybe it doesn't matter, right? Doesn't matter. In some sense, MATLAB prefers one base index. So in some sense, using 0 is bad. So it's okay. U12, right? 12. U13. U14. And then U15. Right? Do you follow me? Or not? And then this is U81, right? U81, U82, U83, U84, U85. And then by the condition, we can determine all these boundary, right? All these are already known. All these are already known, the boundary condition given by the problem, right? Right? All these boundaries are known. So let's examine a few. For instance, what is this value? What is this value because of this condition? 0, right? What about this condition? 0, right? Heat sink, we have heat sink, right? Or we can steam, right? Like keep like 30 degrees all the time. And then what about this value? What is this value? Because of this, what is this value? 2, right? What is this value? So I will use circle to represent the value, right? What is this value? 0, right? What is this value? 0. What is this value? 2. What is this value? 6 and 12, right? And 20 and then 30, right? So we know the values like this. Do you follow me? Then using the stencil, I will not really calculate, I will use the stencil to check the possibility. So all these are known, right? All these are known. All circled things are known, right? All circled points are known. Then using these things, can you calculate this thing? Right? Look at the stencil. Using these three things, you can determine this thing. Using these three stencils, using these 3 points, you can determine this thing, right? So you can determine everything up to this point, and then go up. Using all these 3 points, you can determine this thing. So you calculate the numbers this way. So as I mentioned, you will be extremely bored after doing this, like for various cases. Essentially, everything is identical except wave equation. Except wave equation. Wave equation has repeat points. So we don't have this kind of wiggle room. As you can see, in this stencil, we could go back, right? We could go back. But in heat equation, we cannot go back. Time zero is the beginning. How can you go back? That kind of thing happens. Then we should use that kind of repeated points. But that is too much right now. I just use simple idea over and over again, all the way up to wave equation, and then at that time, I will let you know what you need to do. So please browse these things and check whether you completely understand this heat equation. So 1 dimension, 2 dimension, 3 dimension, doesn't matter. Now I'll raise the dimension. So I will solve the same problem with this instead of just, right? Heat equation in 2 dimensions. So 1 plus 2 dimensional problem. Then, roughly this is the situation. Oh, ut is uij plus 1 minus uij over delta t. And uxx uyy, so we need 3 numbers in this index, right? So I will add one more number. Uij represent spatial variable, and then k represent time minus uij. Do you follow me or not? Do you follow me? And this is I plus 1 jk minus 2 times uijk plus ui minus 1 jk over h squared. So for design, I will use the same denominator. Why should I use complicated things? I will use the same denominator. So delta x and delta y are the same, h. So I will assume that delta x, when I design it, I make this kind of number the same, right? I can design it. Plus h squared uij plus 1k minus 2 uijk plus uij minus 1k. So essentially the same thing, right? And then you can solve this part, uijk plus 1, right? uijk plus 1 equals uijk, and then plus delta t over h squared, and then all these things are written, right? Copied. Essentially the same thing, but now we are very interested in the stencil, right? So I, J, K position is here, right? Three-dimensional object, right? So three-dimensional. This is the I direction, and then this is the J direction. This is the K direction, right? So K direction is time direction. I direction is the X direction. J direction is Y direction. This is the time direction. But in this sense, what happens? We know this value, right? We need to use this value. And then, as you can see, one advanced value in the X direction, right? One advanced value in the X direction, right? And then one behind value, right? And similarly, one advanced value in the J direction and one behind, right? So these things are used to determine this thing, right? So bottom has cross, right? Bottom has a cross. And then top. So stencil looks like this. So we need to know bottom 5 values, right? Bottom 5 values to determine up value. And we go up. Then the boundary condition looks like this. It's like a box, right? Like open box, right? Top lid is removed, right? Open box. So all the boundary and then the bottom is given. But we don't have the top box. We don't have lid, so we determine everything using this stencil and then fill these things. Either X direction or Y, it doesn't matter, right? You fill this thing in X direction or Y, it doesn't matter. But you don't fill T direction first. You should not use a vertical direction first. You fill the bottom layer and then one higher layer than the bottom and then one higher level and one higher level and so on. So you fill these things to come. So as you can see, essentially this thing over and over again about a few weeks until we have finished this thing. So please browse this idea and ask questions. Then we are already close to the wave equation. But if I solve wave equation, some of you are confused between ODE and PDE. Some of you are confused between this and that. So instead of covering wave equation today, I will review whatever necessary here and then answer questions because I don't want to confuse you. If I cover wave equation to this thing, then some of you may think it's too tough. But if I don't cover anymore, you may think this is very easy. You may feel comfortable. Learning curve follows, right? So please browse the idea and check whether you understand the idea and whether you can really implement these things or not. Or if you want examples, then let's spend time on examples instead of studying too many things or learning too many.
Let me see a boundary condition for that one you just put out.
Anything, you can create your own boundary condition. For instance, what about the bottom? So
We basically know the box.
right, we know the open box boundaries. So we know everything in this open box. I mean, on the size of open box, right, or bottom of open box. So, for instance, you can say, oh, this function is like f of xy, right? f1 of xy function, right? Right? You can say this thing. And then you can say, oh, this is like f2 of like something, right? Because one thing is fixed, right? For instance, x is fixed like, right, t and right, y, right? So stuff like that, right? X does not vary t and y. And then here you can also so you can define these things. And whenever the numbers are necessary, we can just plug in the actual position, not the index, but index determines the position. Usually, ij determines jk is not actual point. It means, for instance, xj, yk, or sometimes tj, xk, right? Depending on the dimension and stuff, right? You should not directly plug in ij or ik. Ij are just indices, right? So you should use actual position. So you have this kind of box and then everything there, and then you use the stencil, right? I will show you how stencil is used to create. So we know this value, we know this value, we know this value, this value, and this value, right? That means we know this value, right? So we go all the way. We fill all this layer, right? All the bottom layer, and then we complete this layer. Then it's the same situation, and then we go up. So in this sense, finite difference method shouldn't be very difficult. The only thing that you need to know is the CFA condition. When does it converge? In other words, how to break up. If you break up incorrectly, your result is unreliable. Of course, almost finishing all the cases, even heat radiation, I will give you the chart, right? What kind of thing is required for this type of equation? How to break up the ratio? How many grids are necessary? This kind. So roughly, heat equation is done. But if you still have a question, ask. Of course, you can do 1 plus 3 dimension too, right? X, Y, Z. Then how can you even make sense? It's tough, right?
So far we've done finite difference to the heat equation. Will we do any of the other methods that we use to solve? Like, will we have some sort of like spline surfaces?
That kind of thing is covered in finite element method, but we only handle elliptic equation case like Laplace or Poisson. Because the finite element method uses the variation inequality that has some kind of limitation. So, but in any case, we are using finite difference method to solve all types of questions, and we should know the limitation. And later I will ask you to. In fact, it is already assigned. This is really very interesting. Once you go home, try to check this problem. Initially, we have domain, right? 1 by 1 or 10 by 10, doesn't matter, right? 1 by 1 domain. Then we have M shape, right? We have M shape. It's initial condition, right? So bottom has an M shape. Right? So if you look at the box from the top, you have M shape at the bottom. Then what happens when you solve heat equation, right? So time 0 has M shape with height 1, right? M shape with height 1, but when time is equal to 0.001, what kind of shape will you have? Then you can find this kind of result. Did I use M shape? Because it's symmetric. In addition, I didn't like this pixelation. I might ask E shape or F shape. Let me check. E shape. I used E shape. I should have asked F shape. It's symmetric. It's not very exciting. But F shape might be. This is not symmetric, right? E shape is symmetric. So you have E shape initially. Then take a look. E shape is not difficult to implement. Right? E shape. You begin with E shape. Right, with height equal to 1, right? At this point height 1, at other point 0. So assume that the temperature initially had like 10 degrees here, and then surrounding point is 0. And if we solve heat equation, then what happens? Like you can see the dissipation, right? Dissipation, and then the degree 1, the degree 10 becomes like degree 9, degree 8, and so on. And then the surrounding point may gain something, right? Instead of just a 0, it may gain something. So you may see the heat distribution represented by height, right? Heat is represented by height. And in fact, I might ask animation. Instead of looking strange time axis, in real world, you don't see time axis at all. You can see spatial axis, but you cannot see temporal axis.
And can you like show us how to do that in either Maple or MATLAB? Because I have no idea how to animate a picture or animate a solution.
So we create the information, of course, we create the information frame by frame. So time 0 frame has some kind of information, right? And then time equal to, for instance, you divide the breakup, like 0.001 has another height information. So you create these things in array, and then you convert array to functions. Convert array to functions, and then animate the functions. That's the step. So I will let you know what to do later, but not at this moment. I just want to focus on the pure theory part of finite difference, nothing more than just finite or practical application of this kind. So take a look. What he did was this one. Differential equation became algebraic relation at ij index, right? At ij index, algebraic relation. And right, algebraic relation, and then we determine the length of h and the length of delta t, right? And then by solving this algebraic relation, we eventually solve the differential equation. So this is it. So finite difference is, in some sense, easiest one that you can learn to solve a PDE problem. Of course, people who just self-study these things may have no idea about the design idea, right? CFA condition or the limitation.
Instead of having a bat, like an isothermal condition, say we had an insulated condition, how would we program that, or how would we write that down?
Then we reduce the, so initially what you wanted was the full solution to this domain, right? This box domain. But somehow we should reduce it, right? We should reduce the result. So in other words, the reliable region is this one, and the remaining portion like this, right? The remaining portion like this can be determined by any nice idea, right? The remaining part like this, right? May be resolved by any nice idea. You may extrapolate, you may add more conditions and so on. But reliable steps are these areas. That's the reason why we usually add some condition, like we maintain the temperature like 30 degrees here, 0 degrees here, or all zeros, or heat sink or something. But if we don't have that kind of thing, only thing that we can gain one might be around this result. That's the question. So depending on method, people, because assume that nobody handles this thing at all, then great opportunity to get a PhD, right? Nobody handled this thing before. Then you handle this thing using your eye. But unfortunately, I don't think so. Okay, some people live on this kind of slight, right? Gap, right? But in this course, I don't want to be too specific, right? Too specific. I don't want to care about this kind of small portion in this course. please browse the ideas and ask questions. If you don't, then I will. You may even ask some examples that you want to see. In other words, you want to follow the steps, or you want to really calculate the value. Then I will do, instead of jumping to wave equation, because if I throw in wave equation here, then some of you may be completely confused, because in some sense we covered too many things already.
Well, we could just call it a day.
Instead of calling it a day, I will answer questions. So if you don't have questions, you may leave the room and you may ask any question, even homework questions. What?
For the homework then, number 2.
Number 2. So homework number 4, number 2?
Number 5.
Number 5, number 2? Right? Mm-hmm.
Is that our, is there a specific method where?
System. RK per system. So I will show you what is necessary. So you use this method. So it may take about 10 lines to implement these parts, with about a few more lines to create the loop. Of course, I might use y and z instead of x and y, so you just change this accordingly. So let's return back to check what I used. I used tyz, but I used here txy. So x is y, y is z, right? Oh, no problem. Good question. So collocation method is, oh, by the way, someone asked about the spelling. So let's check the spelling. So I used 2 L's, right? I used this thing. Right, collocation method. So there are 2 L's, right? Collocation method. So when you live in Colorado too long time, this might be tough. So collocation method is the method very similar to power series solution style problem, right? Power series solution. Of course, if you use polynomials. But if you don't use polynomials, then it may have nothing to do with power series stuff. But at least the idea is this. It's similar to finite element in this sense. Oh, it is just, we are saying the solutions are these. And then after assuming the solution, we determine C, right? Roughly this is the idea, right? So in this sense, it is almost the same as finite element. But what things are different? First of all, the basis functions are different. Basis functions phi1, phi2 are different. Second of all, the method of determining Ci is different. So let's do it. First of all, using examples might be better. So let's use an example. So what differential do you want to solve? For instance, if you want to solve this differential equation, and then y of 0 is 5, y of 4 is 11. So assume that we are solving this case. Then we define these things, and then how many do you want? How many do you want? 3. P1 could be defined this way, right? phi 2 could be defined this way. Phi 3 can be defined this way. Right? Assume that we are using 3 basis functions. But if you want to use 5 basis functions, then you can add more functions.
And that's your choice?
Yeah.
So we take
But-
10 if you want?
Yeah, great. So at least use more than 5, please. I don't want to use just one and then. So any questions up to this point? Then next thing is the determination of C1, C2, C3, right? So we want to determine, it's too easy, so I will add more. At least one more, right? This is my limitation of calculation. You will see. So I want to determine, but even this is not easy, right? Also, I will retract myself. My limitation is 2. So C1, C2, C3 determination will do it. Do you follow me? Of course, if you have more basis functions, you need more C sub I, right? Then let's say solution is equal to C1, phi 1, C2, phi 2, C3, phi 3. But because we use polynomials, it looks like this. And as you can see, it looks like power series solution in differential equations, right? This looks like power series solution in differential equations. So let's plug in. What is y of 0? Y of 0 is what? C1 plus 0 plus 0. Right? And given by the problem is the boundary value. What is y of 0 by this problem? 5, right? Oh, we are lucky. We could determine C1. Then there are 2 unknowns. There are 2 unknowns, C2 and C3. So let's determine C3 and C2. So y of 4. What is y of 4? Y of 4 is 5 plus C2 times 4 plus C3 times 4 squared. And this should be equal to 11. Do you follow me or not? Boundary value gives us this kind of equality. So if we have one more equality, then we are done, right? How many unknowns are there? We have 3 unknowns. We have 3 equations. If you assume that you have like 5 equations, 5 unknowns or 10 unknowns, then you may increase the number of these points, right? You can distribute the points in between, right? Between 0 and 4, I use these points. And because there is one more point, what point do you like? 2, right? It's fair, right? Of course, nobody will mind if you use 1. But because between 0 and 4, it's good to use 2, right? I want to evenly divide the space. Why should I use 1 or 3? Right? I should use 2. Yes?
You don't care how many basis functions you use?
So pick at least 5 or more basis functions.
Is there any restrictions on what basis functions you choose?
Usually polynomials might be easiest. But in reality, trig functions or e to the power of ix like FFT might be way better. And in fact, those kind of things are used to solve differential equations called FFT method. But in this course, I don't want to focus on FFT too much. It's not very difficult. It's almost the same as collocation with different fees.
So we can use like 1x squared, x to the third. X
Right. Then it's like power series solution.
Do the fees have to be orthogonal? Is there any restriction on that?
No orthogonality requirement. If you use trig function, you can implement these things, but here, no, just right. Then y of 2, right? Y of 2 will be used, right? We don't know y of 2 is not given by the problem, right? So what you do is this thing. The differential equation, right, gives us the relation. Gives us the relation. So let's do it. Y second derivative is what? C1 plus C2t plus C3t squared differentiated twice equals 4 times C1, C2, C3t. Do you follow me or not? Then what is this second derivative? This second derivative is 2C3, right? And then this one is 4 times C1 is 5, right? C2t plus then we calculate the value at 2, right? These should be equal at point 2, right? So at 2 we calculate this value. So we plug in t equal to 2 to both sides, right? Then the left hand side is this one. The right hand side is 5 plus C2, 2, C3, 2 squared. Then how many equations do we have? We have 3 equations and 3 unknowns. Right? We have 1, 2, 3 equations. We have 3 unknowns. So C1, C2, C3. So eventually we can find all the numbers. So this is it. And if you have one more, we'll assume that you have 2 more functions. T squared, 2 cubed, t to the third, right? I mean, t to the third, t to the fourth. So you have 2 more equations. Then you may use this thing with t equal to 2, t equal to 1, t equal to 3, right? So you have different equalities. Not exactly the same, but you should have addition of c4t, right, cubed, right? c5t to the fourth, and so on, right? This kind. But basis function can be trig functions, right? Orthogonal conditions are satisfied, then we can have different results. So collocation is explained, and if you have other questions, ask me. Anything is okay up to heat equation. I don't want to jump to the wave equation today.
So the only difference between that and the finite element method is what?
Only similarity is this one. Only similarity is this one. Other than that, very different. As you saw, right? It involves integrals. Because some student asked, I will mention about the finite difference method in ODE. Finite difference method in ODE is this thing. We are solving a differential equation on this line, right? From 0 to, for instance, from like 5 to 6. We are solving a differential equation on this line. Then we say that the boundary is given by the problem. Boundary height is, for instance, 2, and then the boundary here is like 7, right? These are given by the problem. Then the question is this: what is the result of this differential equation, right? This is the result, right? Assume that we want to find this kind of result. So this is the differential equation that we want to solve. Then, for instance, y second derivative a plus by prime plus cy equals d. So this is the differential equation you have to solve. Then how can you do it? First of all, we don't know these heights. So we say, oh, the height here is y1, the height here is y2. We evenly divide, right? So it is like 5.1 has height y1, 5.2 has height y2, and then 5.3 has height y3, and so, right? We don't know this, so we name these things, right? y9. Do you follow me? And then we generate the differential equation. So I will make it simple. Assume that we are solving this kind of differential equation, right? Instead of general A, B, C, D, E, I'm just saying this thing. Then, oh, this can be rewritten. This is y at generic position I, right? At generic position I position, y I plus 1 minus y 2 times yi plus yi minus 1 over h squared, right? H is 0.1, right? H is 0.1 squared equals 4 times yi. So I create the relation at I position, right? So I create the relation in this box, right? Then this kind of box can be considered at many other points, right? At this point we can consider the box. At this point we can consider the box. At this point we can consider the box, right? So we consider the boxes at various points, right? So in this sense, how many boxes are there? Total 9 boxes, right? I equal to 1 box, I equal to 2 boxes, 3 boxes, up to 9 boxes. So we are solving 9 equations or 9 boxes for 9 unknowns. So we are solving this kind of equation for 9 unknowns. So this is the finite difference method for ODE. So after solving this for I equal to 1 through 9, we will get, for instance, y1 equals something, y2 equals something, and so on. So finite difference method in ODE looks like. Yes?
Can you write like the matrix system that generates? You know, this linear system?
So let's do it. So assume that, so I will move these things to one side. So what do you get then? Y I minus 1. So I will write in ascending order, right? This one is written first. And then this one, and then this one will be written. So minus 2 times yi, and then this one is 0.0 0.04, right? If you multiply 0.1 squared by 4, then you can get 0.44, right? And then it has minus sign. Plus yi plus 1 equals 0. So essentially you are writing this thing 9 times, right? You are writing this thing 9 times. Then what do you get? You obtain this kind of. So I equal to 0 gives us what? y0 minus 2.04 y1 plus y2 equals 0. And then next thing is y1 minus 2.04 y2 plus y3 equals 0. Right? All the way through, and then yi equal to 9 gives us what? y8 minus 2.04 y9 plus y10 equals 0. And y0 and y10 are given by the problem. y0 is 2, y10 is 9, right? Given 7, given by the problem. So this thing. So this is in fact known. This is 2, this is 7. Do you follow me or not? Then we have a system, right? We have a system to solve. So I will make a matrix. So I will use this space. Then I can move this part to this side. Negative 2, right? I will move this to this side. then negative 7. Do you follow me? So I write a system. Minus 2.04, and then 1, and then 1, minus 2.04, and then 1, and then 1, minus 2.04, and so, right? And then final thing is minus 2.04, and then 1 upstairs, right? And then all others are zeros. Multiply by y1, y9 equals minus 2, 0, 0 all the way through, and then minus 7. So you can create a system and a subsystem. And you can use this idea. Depending on your equations, the pattern may change, right? So by solving this, you will determine y1 up to y9. That means you know the height, right? You know the height. So after determining these things, because you know y1 equals something, y2 equals something, you can just plot these things, right? So it's 5 to 6, and then 2 is the y0 value, 7 is the, right, 2 and 7, but y1 is known, right, y2 is known, y3 is known, y4 is known, and so on, right? So you can plot this. Then this is roughly the result. So this is the finite difference method covered in ODE. Of course, someone who took numerical analysis know how to handle this without using SOR or something. Just fast handling of this tri-diagonal system exists. But you don't have to know it. Just you can ask MATLAB solve this system. Because it's not a question implementing the SOR. This question is solving this or this ODE problem. So you have about 10 more minutes to ask questions. Any question that may help you is okay, yes?
I think I set mine up to do that, and I got 0 for everything, straight 0.
The major reason was this. You might not subtract the end result, end point, right? This point, right? This point and this point. With 0, 0, you will get 0 everywhere, right? Assume that this right side is 0 and 0. You will get something multiplied, something equals 0. So this thing should be 0, right? So the major reason was this. You didn't subtract this thing. You didn't subtract this thing. So if you subtract this thing to create, in other words, you might create the matrix like this, but you should not create the matrix like this. You should create the matrix like this, right?
Yeah,
Then
I'm pretty sure I did that. I had to try diagonal, and I left off the end point.
Then did you use right hand side like this?
I have to go back and check.
Yeah, if you might have 0, 0 here instead of these kind of numbers. Yeah. Yeah, with these things it's impossible to have 0 everywhere. With 0, 0, absolutely 0, 0, right? Yeah. Yeah. Any question is okay, so please.
Just pick points like for the we get the boundary for that co-location example you gave us. We had y of 0 and y of 4. What you have to pick example or in between. You have to pick in between, or can you go beyond? Doesn't matter.
So
The one we did.
So take a look. Assume that you use collocation method. Then this is the idea. Assume that you have like n basis functions, right? N functions, phi 1 through phi n. Then we want to compare the values at how many points? N points, right? So we pick this point, automatically boundary, and then what is the best choice? Do you want to pick all n points around here or evenly distribute? So what is your idea? It's possible to pick all the points here or evenly distribute, so you evenly distribute the points between this and this. So you pick total n points from this to this, total n points between this by evenly distributing positions.
So you give us, when you, like in the homework, you give us y of 0 and y of 1. So if I'm going to use 10 functions,
let me return back to the problem. I want to see the problem and then explain. So
the last one, yeah. So you've got our 2 points are 0 and 1.
right.
So I take point 1, point 2, point 3.
No. You should be inside though. You should be in. So 0 and 1 are boundaries, right? 0 and 1 are boundaries. Now assume that you chose like 5 functions. Then you should evenly divide it. 0.2, 0.4, right? 0.6 and then 0.8, right? Assume that you use 5 functions.
Okay.
So you should not use 2 or 3 there. Yeah, that is for only inside the boundary. You should. Any other questions? Yeah, you have 10 more minutes to ask, so ask any questions.
So the first 3 in the homework, you use the RK4.
Let me look at it just a moment. So the first thing is using RK4, right? Like h equal to 0.1, right? Like space is 0.1. So you use RK4 to determine the next height and RK4 to use and so on.
You should 2-dimensional RK.
Right, 2-dimensional RK4.
What's number 3?
Oh, I said it's 0. This is 0. This is 0. So you should use this thing. So you can convert the higher order dimension, right? Higher order ODE to system. So you should convert this thing to a system, right? And then you should solve a system of first order equation. So you should convert it to a system. Do you follow me? So instead of you are solving second order equation, you are solving first order equation in this kind of system.
We do a quick review of the shooting method.
Oh, no problem. So shooting method is this. Using RK4, we can solve initial value problem, right? So using RK4, we can solve initial value problem. Any questions about this? So we solve this kind of differential equation using RK4. But unfortunately, what we have is this one. Y of alpha is given. Y of beta is given. Boundary, right? Alpha and so alpha to beta we are solving, right? Or t. Doesn't matter. X or t, right? So we are solving the differential equation with this boundary given by the problem. But RK4 is not the one to solve this boundary value problem. RK4 is the one solving the initial value problem like this, right? So RK4 solves this thing, but RK4 does not solve this thing, right? So it's impossible to solve this, but RK4 solves this thing. So this is the idea behind it. So if you have a question up to this point, ask me. So RK4 is used to solve this thing, but it cannot solve this thing. So what you do is this one. The only matter is this one, right? So we guess this thing. So we guess, right? And then solve, right? Guess and solve to determine y, right? And then if you solve, then y beta will be determined, right? Y beta will be some result, right? If we are lucky, this y beta could be the result, the condition given by the problem, right? If you are lucky. But we cannot expect this kind of law. In other words, we will get some result that may be bigger or smaller than the number given by the problem. So this is the situation. Our goal is finding this one, but our result after solving RK4 might be this. In other words, there should be a gap. So we are narrowing the gap gradually. In other words, our guess might be too big. Our guess might be too big. Then we reduce the guess. In other words, instead of our guess 1, our guess 2 might be guess 1 minus guess like 1, right? Or something, right? So in some sense, I will use the same guess variable, and then guess might be guess minus, for instance, 1. Our guess changes. And then after changing the guess, we reshoot, right? We reshoot, and then we may not hit the target, right? We may undershoot. Then something might be overshoot, something might be undershoot, right? Then we will reduce this gap by bisection. That's the idea. In other words, our guess starts at some overshoot and some undershot, right? And then we narrow this guess gradually.
You just narrow it until you've gotten within...
Close, right? Some right. That's right. So 3 more minutes and final opportunity to ask questions before we can then let's finish it. Have a nice weekend.